We've done recurrence relations before. When I have a sequence that determines the next one by looking at some of the previous one. Is called a recurrence relation. And depending on how far back we go, we can define a recurrence relation of a certain depth. If we go back 2 steps, that's a depth 2. 3 steps, depth 3, and so on. And I go back as far as I want. I could maybe only go back 1. But the reason for these recurrence relations is to determine some sort of rule for the sequence. Here's a setting where I might see something like that. The number of bacteria in a dish double every hour. And we start with 100. Now, excuse me, you could actually be counting individual bacteria. There are 100 individual cells in this petri dish. You could be counting the size of the colonies of bacteria. There is a total of 100 square millimeters occupied by the bacteria in this petri dish. But I'm going to start with the idea of 100. But if that is turned into a sequence like this, then I really want to say that the number of bacteria at our n is given by twice the number that came before it. As long as I have this piece of information somewhere, and then I remark that this holds for n bigger than 0. I can use recurrence relations to model real-life situations, like this one. Now, my eventual goal is to take what is currently a recurrence definition, a recursive definition, and turn it into a non-recurrent solution. It would be nice if I could tell you how many bacteria there will be after 312 hours without having to do from 0 all the way up to 312, right? But I actually want to start with the idea of where am I going to be able to use such a situation? Where am I going to find these sorts of behaviors? I've got an example for you that I know you've seen. In the 13th century, Leonardo of Pisa wrote a book called Liber Abaci, the Book of Counting. Book of Counting. In which he said, I've got a pair of rabbits. And I'm going to put an ideal situation on these rabbits. When they are less than a month old, they can't breed. Or less than 2 months old. But as soon as they're 2 months old, they can breed. And gestation is exactly a month. Now, the pair of rabbits I have are exactly one male and one female. And I'm going to rig this so that when the rabbits that bred give birth, they always give birth to one male and one female rabbit. How many rabbits do I have at the end of a year? Assuming no predation and no death. Or nothing's going to eat these rabbits and they're not going to die. How many rabbits do I have at the end of the year? How many rabbits do I have at the end of 2 years? Bottom of page 534. At month 0, I have one pair of rabbits, and they are too young to breed. At the end of month 1, I have one pair of rabbits, and they are too young to breed. But they're 2 months old here, right? Oh, they can start. A month later, they give birth. These rabbits are too young to breed. But these rabbits, which are now these ones from up here, they're old enough, they can breed again, can't they? So these rabbits wait, they go another month, and they give birth to another pair of rabbits. Now, one of these is old enough to start breeding at the end of the next month. They give birth. This one is too young. These two are newborn. I have a pattern to the number of rabbits here. Leonardo said, hey, wait a minute. After 1 month, I have one pair of rabbits. I started with one pair. They're too young. They can't breed. At the end of month 2, but now they're old enough, they have sex and start to get pregnant. At the end of month 3, what happens? Well, the current pair gives birth to another pair. Now, these are too young, but these aren't. These are adults. So they have sex again. And at the end of a month, that pair gives birth to another rabbit. This one just carried down, this one just carried down, and this is my new pair. Right? But if you think about it, this is really, these two rabbits didn't change, and this one got added. But now at the end of month 5, these rabbits were newborn here. They had all of month 3 and all of month 4. They're old enough to have sex. This rabbit and this pair of rabbits, these two pairs, they have sex, which means at the end of month 5, they will give birth, won't they? So from these two, I'll get 2 more. I already have rabbits, and then I'll get 2 more. These rabbits are all already now old enough to breed. So I have 5 rabbits. All 3 of these pairs get together and have sex. And that means at the end of month 6, I'll get 3 more sets of rabbits, won't I? From what I already have. Hey, wait a second. Do you see the recurrence that's going on here? The number of rabbits from 2 months ago are all old enough to give birth. So that's what's causing this. But then all of these rabbits are still here. So I have to, in month N, I have to look back at however many rabbits were in month N minus 1. Those are the ones that are already there. And however many were in N minus 2. Now, you may not recognize Leonardo of Pisa's name or the book Liber Abaci. But will it help if I tell you his father's name? Leonardo's father's name was Bonaccio. Leonardo, son of Bonaccio in Italy. What's son in Italian? Just as in Arabic, al is used as a patronymic indicator. It indicates your father's name. Fi, F-I, is used in Italian. Leonardo Fibonacci. Fibonacci. This is my Fibonacci sequence. And if I write it in this recurrence format, I end up with a statement that says, oh, at 1 month, I have 1. At 2 months, I have 1. And for every month bigger than 2, I can use this. Now, some versions actually write F0 is 1 and F1 is 1. And then this is for n bigger than or equal to 2. It's the same workout. So here's an idealized situation where I have to realize what's going on in terms of the depth of my recurrence. Questions? In the late 19th century, a puzzle was developed. The puzzle consisted of a set of discs, with the largest on the bottom getting smaller as they go up. You could think of them as coins with holes in the middle. And you put the largest one on the bottom, and you have to always keep smaller on top of larger. You can never put a larger disc on a smaller disc. You have a stack of these discs over here in column number 1. You are only allowed to move 1 disc at a time. I want them all to go here. Doesn't seem like a difficult thing, right? If I have 1 disc, how many moves does it take? Piece of cake, right? Now, the unfortunate thing is that I forgot I was going to do this puzzle today, and I only have two discs that are the same size. So we'll make believe that the one on top at the moment is smaller. If I have two discs, how many moves does it take? Why? So I have to move the stack on top here. That takes one move. Then I have to move the last disc over, and then it takes one move. If I think of the discs as the top disc and the bottom disc, then I can kind of write this like this. You move the top disc to peg 2, if they're 1, 2, and 3. I move the top disc to peg 2. I move the bottom disc over to peg 3. Then I move the top disc to peg 3. I don't have a third coin. Does anybody have a coin? I got it. We'll use that. Why?
You top one to the far right, the middle one to the middle, and then top one to the middle, the bottom one to the far right.
Hang on a second. I moved this whole stack to here. Moving 2 coins takes 3 moves. Then I move this one. 1, 2, 3. So I had to do this to move these 2. Then I had to move this one all the way over, and then I could move those, right? And I'm going to write it like this. I move the top 2 to peg 2, 3 moves. I move the bottom to peg 3, 1 move. And then I move the top 2 to peg 3, 3 moves. All right, wait a second. If I had a 4th disc, it's got to be a big disc. I'd have to move all 3 of these off of it, then move that disc, and then move all 3 of these back onto it, right? 7 and 1 and 7. Huh. Because of the time in which this occurs, the late 19th century, there is a fascination in Europe with the Far East. This puzzle, developed by Edward Lucas, is called the Tower of Hanoi. So I'm going to call the number of moves for any number of disks, I'm going to call it H whatever. So right now I have H1 is 1, and H2 is 3, and H3 is 7, and H4 is 15. But think about the way we built H2. We really used H1 to build it, didn't we? We had to move the top one disk, then we had to move the bottom one disk, then we had to move the top one disk again. So it's like I said to myself, here I moved these. Well, that's 2 disks, that's H2. So to make H3, I really did H2 plus 1 plus H2. And to do 4 disks, I wrote it here, H3 and 1 and H3. So here's my recurrence. As long as I have H1 being 1. Bottom page 535 has a picture. It kind of looks like that kindergarten toy with the donuts of all the different colors stacked on a peg. Same idea, only we just have multiple pegs. All right. I'm going to think of this like a programmer. I'm going to think recursion. If I want to calculate Hn, I'm going to build this. Here's my iterative behavior. H1 was 1. H2 is therefore 2 times H1 plus 1, which is just 2 plus 1. H3 is 2 times H2 plus 1. Okay, wait a minute. I'm going to multiply this 2 in. 2 squared plus 2 plus 1. I didn't write it as 4. Don't panic. I promise there's a reason. What's H4 when written this way? Well, it's 2 times H3 plus 1. If I multiply that 2 in again, I get 2 cubed plus 2 to the second plus 2 to the first plus 1. Which is 8 and 4 and 2 and 1. Binary, 8 and 4 and 2 and 1. 15. What's H5?
The 2 cubed plus 2 squared plus 2 plus 1, 2 times that as well.
Which is 2 to the fourth plus 2 cubed plus 2 squared plus 2 plus 1. 16 and 8 and 4 and 2 and 1. 31. I got a hunch. Chapter 2, Section 4. Sequences and series. This looks familiar. Let's flip back to Chapter 2, Section 4. And we were given a list of a whole bunch of sequences that it might be useful to remember. And I look at this list of numbers here, and I start comparing it to the lists of numbers I see here. Page 175. What do you see that looks really, really close to, but not exact, to our sequence? My powers of 2 go 2, 4, 8, 16, 32, 64, 128, 250. I'm off by exactly 1 each time. And I'm always all the same direction. This is 1 less, isn't it? Think about this in binary. That's the reason I wrote it like this. In binary, this is the number 11111. And if I added 1 more, I'd roll over all the bits, wouldn't I? I'd get 1 0 0 0 0 0. 2 to the 6th. 2 to the 5th. And 1 more would give me 32, wouldn't it? As a matter of fact, this is true all the time. As a matter of fact, then I can say that Hn is going to look like that. And I can show that this is 2 to the nth minus 1. Hey, guess what? We turned a recurrence into an explicit formula. If I now ask you how many moves does it take to do 12 discs, you can just plug in 12, can't you? I turned a recurrence into an exact formula. We have solved the recurrence. Now, because Lucas was a mathematician by trade, he didn't particularly care about the puzzle itself. So somebody took this mathematical curiosity and wrote it up as if it was happening in the far mystic East. Here is the legend behind this, the myth. There are, in a hidden temple in the mists of Hanoi, a tower made of 64 gold discs. Each disc smaller than the one it stands upon. The monks are charged to move 1 disc a second. When they finish, the great cycle of the universe will be over. How long do we have? Wouldn't that make for a hell of a sales gig? Do it with 5 discs, show people how not easy it is, and then imagine 64. How many moves is it going to take for 64 discs? (1.8 times 10 to the 19th seconds. Okay, wait a minute. 1.8 times 10 to the 19th in seconds. Y'all have your computers and your phones and stuff. I need you to Google something else for me. What is the current age of the universe in seconds? 1.8 times 10 to the 19th turns to do 64 disks.
436 quadrillion.
Quadrillion. Quadrillion is 10 to the 17th. In other words, it's going to take about 42 times the current life of the universe so far. We got plenty of time left. By the way, what if instead of 3 pegs, I give you 4? Evan, the solution you presented to me, where you said, first I move these, then I move the bottom one, that's actually the best, most efficient way to do this. It's the smallest number of operations it takes. It's the most efficient way with 3 pegs. We can show that is the lowest big O we can get. It's exponential. This is a big problem. If I up the number of pegs, nobody knows whether or not an optimal solution exists for any number of disks. I can always just ignore one of the pegs and do it was like 3 pegs. And then I'll get this solution again. But if I must use that other peg at least once, no one knows whether or not there is an optimal algorithm for solving that one. Reeves' puzzle is still open. Questions? I'm going to give you a grid. Listen to me. Now I'm a crap artist, so we're going to make believe this is the right line. That's the diagonal of our grid, right? You start in this lower left corner, you end in that upper right corner. You are only allowed to move right or up. How many different ways are there to get from here to there without ever crossing that diagonal line? You can land on it, but you can't cross it. That's a weird idea. Here's another weird idea. I give you numbers. Right? I have a list of numbers. And I want you to multiply them together. But I know the way your computer works is it can only multiply two things at a time. If I give you one number, how many multiplications do you have to do? 0. You're done, right? If I give you two numbers, you have to do one multiplication. If I give you three numbers, how many multiplications do you have to do? But you can do those in different ways, right? You could multiply x1, x2, and then take that answer and multiply by x3. Or you can multiply x2, x3, take that answer and multiply by x1. So really, I can think of this as having one way to do it. So I'm just multiplying the two numbers. But I can think of this as either this or this. Now I give you four numbers. How many multiplications do you have to do? How many different ways are there to do that? Well, I mean, I could do that, right? But I could do this in two orders. So I could take this one and then do x4. Yes? Or I can do numbers 2, 3, and 4 first and then do x1. Right? So I did numbers 1, 2, and 3 first, and then I did number 4. But I do numbers 1, 2, 3 two different ways. I did numbers 2, 3, and 4 first, and then did x1. But I can do 2, 3, 4 two different ways. There's one other option I missed that's not here yet at all. I can multiply the first two numbers. I can multiply the second two numbers. I take those two answers and multiply them together. There are 5 different ways to do this. This pattern actually requires me to recurse all the way back. Notice that C1, the number of ways to do number of ways to do one number is 1, right? There's one way to do it. You don't do anything at all. So let's call Cn the number of ways to insert parentheses in a list of n plus 1 numbers. So C0 is 1. A list of one number, you don't insert any parentheses at all. One way. An empty way, but one way. If I only have 2 numbers in my list, then There's only one way to do it, the way we showed right here. But if I have a larger number, then I need to think about all the ways to do one less, and then add on one at the beginning. So I could say, oh, I'm going to do one at the beginning, and then I'm going to do the rest of them. That was these two ideas, right? I did one at the beginning, then I did the rest of them. One at the beginning, and I did the rest of them. Or I could say, or I'm going to do two at the beginning, and then look at the rest of them. Or I could do three at the beginning, and then look at the rest of them. Or I could switch the word beginning and end. And that's the difference between this row and this row, was whether the extra number was at the beginning or at the end. At the beginning or at the end. This is a complete depth recurrence. In order to know how to do n, I have to know all the numbers that were in front, not just one or two or a couple of them. To know all of them. In programming terms, this is a full stack requirement. You ready for the weird ass part? This number is the same as this number. C4, 4 by 4, sorry, this is C5 because it's 5 over 1, 2, 3, 4, 5. 5 over 5 up. Those are the same numbers. This particular relationship, these are called Catalan numbers. There is a very interesting method for solving problems involving stacks like this that involve something called generating functions. Generating functions is a calculus-driven topic where we try and find a function whose expression as a polynomial has the coefficients that match our sequence. There's a function whose coefficients are the Fibonacci number. There's a function whose coefficients are the Catalan number. There's a function whose coefficients can generate just about any series we want. But the theory of generating functions is a piece of functional analysis, which I find really interesting. It's really Dr. Burns's area of focus. I don't know how much actual generating function work he did. The most amazing use I ever saw for generating functions, and this idea in general, was from a graph theorist at the University of Pittsburgh who was trying to generate the different numbers of isomers in long chain hydrocarbons and to determine if the isomer structure changed the boiling point. And the answer was yes. Well, the generating function is psychotic. It was an amazing paper. Dr. Glenn Whitehead at the University of Pittsburgh and Dr. Kim Birch at IUP worked on that while I was in grad school. It was an amazing piece of work. It turns out that this is exactly what recursion does for me in computer science. If I want to build a recursive algorithm, it makes sense to go, well, what if it was smaller? Can I break it into smaller pieces? Can I look back a step or more than one step? This is what the strong mathematical induction argument is about. If I have to look back more than one step, that's a different induction hypothesis. But the principle still works. Dynamic programming is all about allocating resources appropriately to break it down into simpler problems. Tuesday, Tuesday is the celebration of scholarship. There are a whole crap ton of talks going on. Scheduling talks, given a finite number of rooms to put them in, and different lengths of times, different starting times and ending times, how do you put things in the right places? Scheduling tasks are best accomplished in dynamic programming terms. They use this sort of recursive behavior. This is example 6, page 540 to 542, and it even provides me the actual algorithm. And what we do is we figure out which talks can be made compatible based on when they start, how long they are, attendees required, so I know which room they need to be in. And then I can figure out which talks are compatible, and then I can determine from that maximum number of people that can go to all the talks. And thus I can schedule. Now, I'm pretty sure that's not what we actually did for the celebration of scholarship on Tuesday, because the communications class was working on the layout and the scheduling. They're not geeky enough to write the programs, in my opinion. But I think it would be a really nice way to do something like this. Questions? I know it's a rare occurrence, but if you get on 66, down here off of Route 30, there's a toll plaza. And now that everybody has an easy pass, nobody actually carries money for the tolls. But that was not the case when I started working here. That was a cash toll plaza. It was cash only, and there were no people there. You could only pay the toll in 1s and 5s, depending on where you were coming from. It would always be an increment of dollars. How many different ways can you pay it? If you owe $3, how many ways can you put money into the toll booth if the order in which you put things matters? Now I'm going to be sneaky. I said you could only pay with 1s and 5s, right? That's $1. And so is that. If you owe $3, how many ways can you put it in? I could have 3 coins, right? I could have 3 bills. I could have any mixture of those, right? And I could put them in different orders. A lot of orders, isn't there? That's a recursion. Because as soon as I say, well, now you owe $4, how many ways can you put it in? Well, that's all the number of ways to put in $3 plus 1 more. And it could be the first or the last. Well, really, it could be 1 bill or 1 coin. So it either goes here or here. Oh, so I've got 2 options times the number I already did. There's my recurrence again. As soon as I get to 5, something weird happens, because then I can use a $5 bill, right? So I have to add on more things. There's another or in there. There's a new option. Okay, personally, I don't care about paying tolls all that much. But the idea that I can use this to generate a recurrence, and then from that recurrence, find a formula. My goal, starting Wednesday, is to figure out how to do this. I want to be able to come up with a formula for the Fibonacci numbers, so I don't have to calculate all 100 of them to get the 101st. But that's not Monday, because Monday is the exam. I will post the homework key and the review sheet key. If you have questions, please email me. Otherwise, I will see you all on Monday. Have a wonderful rest of your day and a good weekend.